today, I'm going to talk a little bit more about how we protect the memory from the outside of the computer from the programs that are running inside of the chip. Now, we've talked before, and we sort of said that there is a sort of supervisor mode where the CPU gets to do things that normal programs aren't allowed to do, and that kind of gives us a protection between code that I write that's terrible and buggy and crashy, and code that the operating system provides that is perfect, never goes wrong, mostly doesn't go wrong, and more importantly has the keys to the castle and can control things like my hard disk controller, my floppy disk controller in the kind of world that we're in right now, those kinds of things. So how do we protect areas of memory? What I sort of mentioned before is that we sort of have like a bouncer robot at the outside of the room who looks at the address and says, nope, you can't read that because you don't have the pass. That's a huge simplification, like all of this. What do we call it? They call it the noble lies, I think. Every time physics, they'd say like, we taught you this thing last year. That's not how it works at all. It was a simplification.
Let's start again.
So we start again. So this time around, instead of just having our bouncer robot who is just checking, can you read or write to this address? There's actually two things that are going to go on, because we discover along the way that actually having an extra ability is very, very useful. Now, we'll talk about that ability in a second. So what I was going to do is I was going to suggest that our computer, maybe let's say it has 1,000 cells of memory, or 10,000, sorry. Yes. And what we could do is have literally 10,000 entries in a table that says yes or no. And then every time I go to read a single cell of memory, our bouncer just checks to see, cell 937, yes, no. No, you're not allowed to read that one. Okay. That would mean, though, that our bouncer would need as much memory to store whether or not you can read or write as there is actually memory on the computer. And that seems a bit of a waste of memory, or else, we're going to have as much RAM for access control as we do for actually storing useful data. So the first thing we're going to do is we're going to simplify things, and we're going to say, let's group chunks of memory together and say this, we're going to treat it the same way. And so I'm going to use in my simplified computer, I'm going to use every 100 cells of memory are going to be treated the same. So that means that if we have an address that is like 1, 2, 3, 4, I'm going to say 3, 4 here reference into one chunk of memory, the 12th chunk of memory. And so that chunk, we can, to do our good old-fashioned pigeonholes, is going to be a 10 by 10 chunk, which gives us 100 possible cells. And I could pretend to draw 10 of these. Imagine there are 10 across there and 10 across here. And so the 3, 4 picks the third one down, the fourth one across, say. So this is what we're going to be reading and writing to. And this is the 12th bank of these cells. We call these pages. This is a page of memory. And so this is the 12th page of memory, and we're going to read the 34th entry of that 12th page. And this whole page is either available to me or not available to me. So immediately we've reduced the amount of information we need to store to say, can I read it or can I write it or can I look at this memory, down to 100th of what it was before, because we're going to treat all of these the same, all these cells the same. So if we imagine we have 4 digits worth of address, so we can only go from 0000 to 9999, so that's 10,000, then what we need is 100 entries that correspond to the first 2 digits that say whether or not I can read or write to that piece of memory. So our bouncer robot only needs 100 entries. That makes it a lot easier. Now, of course, it would be inconvenient to have 100 little pieces of paper inside the robot, as it were, for each individual slice of memory. So where could we possibly store the information about whether we can read or write to a piece of memory? Well, we've got 100 of them. How about we just use one of the pages of memory here as the list of whether or not we can read or write to memory, right? It seems like makes sense. So now, effectively, let me put over here, our robot over here who's going to check to see whether or not we can access memory or not. So he's going to...
There's obviously
yes or
an
no.
easy joke here about how the bouncer's not got as big a head or brain as some of the other robots.
But we're not going to make that. We're not going to make that joke because he's actually more sophisticated. I'm doing him a discredit by just saying that he says yes or no. Your name's not down. So the bouncer has one piece of information. That is which page of memory his table is going to be stored in. Mm-hmm. So let's say over here we've got our RAM chips that look like this, like little spider things, right? And so out here, these are the addresses of the memory that we're actually going to go and read and write to. So this is, let's say that's page 0. They don't have to correspond to the same thing. That is, a page does not necessarily physically correspond to a particular RAM chip on the outside. Well, but let's say each of these chips is one of those, 10 by 10 pigeonhole tables out here. Mixing all my metaphors.
I'm with you.
So the robot, the one thing that we have to configure the robot is which of these pages is he going to look into for his yes/no table. And so we'll just tell him, hey, you're looking at a page 0, physical page 0 out here. So an address comes in, or 1, 2, 3, 4 comes in. The robot ignores the 3, 4, looks at the 1, 2. He knows that he has to read from page 0, the 12th entry, so that's whatever this one is over here, 1 down, 2 across, and it'll say either yes or no. I know I'm just going to wave my hands a bit here and say that the number that's stored in there somehow encodes whether or not we can read and write of it, and whether or not that's okay for us as a user program or whether it's okay as the operating system program. So they could have different permissions. If you're the operating system, maybe you can always read it, but if you're just a user program, you can't. So that's the first thing the robot's going to do. And that makes a lot of sense. And with 4 digits worth of address, we get to use one page to store all that information, and the other 99 pages that we have are available to use for us in our program. So that seems like a decent trade-off. That's like 1% of the memory is used for this purpose. And now we've got pretty general protection. Now, the other thing that it turns out it's very useful to be able to do is to actually remap the addresses that are coming from the left-hand side. So off to the left here, we could have to imagine that we've got our little computer with his abacus robot over here who's saying, I'd like to read and write memory, and he hands the address to the bouncer robot, and he says yes, no. But also what he can do is he can change that address. He can say, you read from address 0, but address 0 is where my tables are. So I don't want you to actually read from physical address 0. What I might do is say that address 0 corresponds to the first page of memory over here. Now that doesn't make so much sense when we only have 4 digits worth of address, right? Why would you want to mix it all up? It seems very, very confusing, right? I get that. But if we think about modern computers for a moment, I know I keep changing back and forth between these older, simpler ones. You're probably aware that most computers these days are 64-bit computers. That means, to a first approximation, what that means is most of the operations that they do are on 64-bit values, and they use 64-bit addresses. So that means that they would have quite a few digits in their address here. If in binary, 64 of them. In decimal, it's 16 exabytes worth of data, and an exabyte is 1024 petabytes. 1,000 of petabytes, 1024 terabytes. Terabyte is 1024 gigabytes, and then megabytes, and then kilobytes, and then bytes. So that's an awful lot. So that means that we have far more addresses available to us than there is any amount of computer memory you could plug into your computer, right? I don't know what your video editing system has got, but it's very unlikely to have more than, say, a terabyte of RAM, and I'd be surprised if it even has that much. This laptop, I think, has 64 gig or 128 gigabytes of RAM, which is like 100,000th% of the available space for addresses. So that means that most of the addresses don't do anything useful. So why might we want to change the addresses that our program sees to correspond to different physical addresses on the outside world? Well, 2 reasons. One, we can now take advantage of that 64-bit address space, or the bigger address space, to actually partition the world into this area of memory is all about talking to peripherals, right? So we always mean that when you talk to this address, it always means peripherals, and this area of memory over here always corresponds to program memory. And of course, in like a modern computer, again, you're plugging in physical chips onto the board, these DIMMs and SIMs, not SIMs, but DIMMs anyway. And it's not necessary that those physical addresses that those chips have correspond to a contiguous range of values, right? It may be that you plug it in and this one has address 8 million, and this one over here you plug in, it's now got address 24 million, just because that's the way the physical wires on the board work. So it's very convenient for the operating system to paper over that and say, no. From a program's point of view, addresses start at 0 and go up to 1 million. And that's very, very convenient. It lets us write a page table in this robot that says, when you read address 0, I'm just going to hide the fact that actually goes onto this RAM chip here at this particular a physical address.
Am I right in thinking if it's 64-bit, it's 2 to the 64? That's the number of addresses.
That is the number.
Because I just chucked it into my phone while I was...
Yes, so that is 16 exabytes worth. That's the only thing I remember it as. I don't know, it's just got so many digits, it's like almost mind-bogglingly high to understand. And so, that it makes sense to have some scheme for like saying, well, this big address space is convenient and useful and everything, but we want to map it down to just a set of sensible chips, addresses on physical hardware. And then there's another really important thing that we can do. Once we have this capability of mapping the addresses that our program generates to the physical addresses that go onto chips, and that is when we want to run more than one program at the same time, we can arrange for those programs to... the naive way to do this would be to say, like, okay, program A, you start at address 1000. Okay, program B, you start address 4000, and let's hope they don't crash into each other. And then when we switch between program 1 and program 2, when you like Alt-Tab in your Windows, then we're running the code that's either address 1000 or address 3000 or 4000, whatever it is I just said, right? And that's great, and that's fantastic, but then what happens if I load another program that you've written, Sean, and on your computer you've decided it's the second program, so you wrote it to work at address 4000, and now suddenly I can't load it into my computer because I've got my own program at address 4000. I want to load it at address 8000 or somewhere other different place. Basically, everyone has to agree ahead of time where all their programs are going to go. Now, with 64 bits worth of space, you could reasonably pick enough random locations that your programs don't overlap, but that would be very inconvenient. And so what the operating system does is it papers over even that. Every program thinks that it has all the memory to itself, and that it always starts at address 1000 or 10,000 or whatever. Each operating system will pick a different sort of starting point, but it'll say, yeah, you load in at address 1000 and you run. And as far as you're concerned, that's the place where you live. Now, that's not true because you might be in some physical location that's completely different, but you can't tell the difference because every time you give an address to the outside world, our little bouncer robot rewrites it to go, no, your program A, you're going to go over to this physical area of memory. So that makes... I'm sort of trying to build a case for why this is a useful and a valuable thing to be able to do. But now we kind of need to explain how we can extend our robot to do that. Now, first of all, naively, for each of these slots in the page table, we can say not only is it readable or is it writable, but you can also say which real page number it is out in the outside world. So that's an easy thing. The second thing is, though, that we've just described that this is only valuable when you have more addresses. And if I wanted to have the address 1, 2, 3, 4, 5, 6, 7, 8, and I'm carefully counting how many digits I've written down here, with the scheme I've just described, this part of the address is the part we need to look up in our 100 entry table. Well, that's a bit bigger than 100. So either we need to make our table a lot bigger or something else has to happen. The observation that we're going to make here is that we can't have this huge chunk to be able to map it. The way that we're going to solve this problem is we're going to make the observation that most of these mappings are incredibly sparse. Most addresses in this huge space don't map to RAM. It's an error, right? Address 997643 doesn't map to RAM. In fact, nothing beginning with a 99 might not map to RAM. And so how might we take advantage of this? And so the best analogy I've got for this is, do you remember the old, I think Sir Ian Livingstone, choose your own adventure books? Yeah, turn to page 7. If you've got the amulet.
Hang on.
Oh no, you're actually going to go and find one.
The very first one in the series.
The dog went and barks. Look at that, the Warlock of Firetop Mountain. I have such fond memories of that. This is signed. Amazing, you do remember the Choose Your Own Adventure or Fighting Fantasy books from like our youth, which I think nicely ties in. We started this whole journey of discovery using the books that I grew up with, the Osborne books with the little robots, and now we've sort of moved on to Choose Your Own Adventure. So what we're going to do is kind of a Choose Your Own Adventure. And so our robot is going to break, the bouncer is going to break the address up into 4 components. We've got the 7-8 at the end, which is the like address within the page, just as it was before. And then I'm going to call this CC, BB, and AA. These are the other parts of the address, AA, BB, CT, and then obviously your offset in the page here. And we're going to say, okay, now the 0 that we've got inside the robot here, which corresponds to the sort of starting page of our whole adventure. And so we're trying to look up this number 1, 2, 3, 4, 5, 6, 7, 8, this address. Where do we actually go? And so we turn to page 0. And in page 0, we have this table of 100 entries. And the 100 entries correspond to the first 2 digits of our address. And each entry can either be, you're dead, stop. That is, there is no memory here. End of your adventure, sorry. You know, which will mean in this instance, like page fault, there's no memory, segmentation violation, and blue screen of death. Any, whichever thing makes sense for whichever operating system you're in. Or it can be, no, for entry 1, 2, turn to page 77. Ah, okay. So what the robot then does is turns to page 77. So we go dot, 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 dot. And somewhere down here, we've got our chip here, which obviously has another 100 entry table in it. And now, unsurprisingly, we're going to look at the next 2 digits, 3, 4. And so 3, 4 is going to index into this table. And then again, we might discover, no, this memory is not mapped, end of story. Or it may say, no, turn to page 22. Page 22 is going to be over here. And we follow our chip here. And then finally, we're going to look up page 56 in this table here. And instead of saying, and now turn to page whatever X and look up further, this is just the final destination. This will say, this memory 1, 2, 3, 4, 5, 6 maps to physical page 99. So 99 comes down here. So he has in slot 56, he has an entry 99. That points him down to the page down here, 99. And now we just look at the 78th entry in here, and that's the value that we're going to return back to our robot who wanted to read address 1, 2, 3, 4, 5, 6, 7, 8. So it's a lot more involved, but we only need as many populated tables as there are sort of prefixes to the address. So in this instance, we have the 1 page at the beginning, and, you know, maybe on our particular choice of computer, only the first 16, 17 addresses make sense. And so they will point onto a new page, a different one each, but all the other ones will say, no, we're done here. Stop talking. You know, this is the end of it. And then similarly for each of the other pages. Now, on a modern computer, so obviously I've done this with 100 here, right? And these separable bits here, and we've broken our address into 3 pieces. On a modern x86 computer, as I said, we have 64 bits in total. And typically, it's configurable, but typically we use 4 kilobyte size pages. So 4096 entries at the very end are the correspond to the offset. And then different numbers, maybe 4 or 5 lookups along the way using different chunks of address space to look for it. So instead of just having 2 digits here, there may be like 8 binary digits, so there's 1024 different entries, that kind of feel. And each CPU does this differently, and it's often configurable. It does mean that still there's quite a lot of memory is being given over to this mapping table, and so that is actually a relevant consideration. It's like a non-trivial percentage of my computer's memory is taken up with all the different mapping tables for all the different processes that are running, but it gives me so much flexibility. So just to sort of finish off this theory, this thought here is that, like, what that means now, if you think about it, is that in order to read or write to memory, our CPU robot over here has said, hey, I'd like to read address 1, 2, 3, 4, 5, 6, 7, 8, hands it off to the bouncer robot, who then has to read 1, 2, 3, 4 memory locations to actually discover where he should be reading my value from, which seems like a huge amount of extra weight. Now, we're always told that memory is slow. We've talked about it before, right? Like we go to great lengths to try and hide how slow memory is. And we've just made it so that every access takes like multiple actual reads of, which seems daft. And so, like so much of computer science, we solve the problem by adding a cache, right? There's almost nothing that can't be solved by adding another layer of caching. And so what our robot has is a little cache of the last few addresses that he's looked at. There's like 64, 128 kind of entries over here, and he remembers the mapping for page 1, 2, 3, 4, 5, 6 and just notes it down in here. And so before he goes to this long walk of like following the pointers from slot to slot and RAM chip to RAM chip, he'll quickly see if he's done this one before, and if so, we're off to the races. He just needs to go straight to the right answer at the end here. So this thing over here is called a translation look-aside buffer, or TLB, and it's one of the sort of like more surprising caches when you're doing performance analysis work and things and the stuff that I do in my day job. Sometimes you can hit this as being the bottleneck. It's like sometimes if you're jumping all around memory, even if it's in the CPU cache, like actually available to the memories available to read quickly, you can't actually map the address from your logical address to the physical address fast enough, and this becomes a bottleneck. So it's always fun to discover these things.
So you've got these 4 jumps. Will you always have to do 4 jumps to get to your memory in this instance for this example? In
the way that I've configured this, yes, up to 4, right? In order to read the memory at the end, we need to have gone through, I suppose it's 3. It's 3 jumps, and then the 4th one is the actual read of the mapped memory. And so, yes, that's why we need this TLB to kind of hide that away. It will finish early if we know for a fact that there is no memory there. So, for example, if my computer, I've decided in my operating system that addresses 00 ... all the way up to 20 ... this corresponds to memory somehow, but addresses 21 ... through to 99, there's just nothing there. Then in my root table, that very first table I've got, I'll populate the first 20 or 21 entries with pointers to the next slot, and they'll all need to be their own separate tables, so there's another 20 tables worth. But from 21 through to 99, to get rid of most of my memory, I just say there is nothing here. I just put a 0 in that table entry, and it means that if you try and read address 21, 21, 00000, then immediately the first walk says, nope, this is it, we're done here. And so what we've really done is we've built a tree in hardware where the first is a 100-way tree, and the first entry points to the next 100-way tree, or it points to null, do not go here. So it's a bit, if you were to get your fighting fantasy book and sort of draw through all the pages and which ones turn to which.
I think there's a number file on this,
I think there is, actually. I think you're right. Yeah, I think they did a whole thing on it because there's a lot of graph theory behind it. Now, with the Final Fantasy things there, what they're trying to do is to push you back onto the same narrative so they don't have to have this huge fan out. Yeah. And that's cool and interesting. And typically, we don't do that with memory tables, but we can. So what that means is we can actually map different parts of the address space to the same physical memory, and sometimes that's really, really useful. For example, if you have the screen, the video memory of a computer mapped in a particular location, as you write off the end of the memory, what you might want to do is go back to the beginning of the memory. And so what you can do is map a second copy of the memory so that when you write to the address past the end, it actually starts again back at the beginning. There's some really little nice tricks that you can do that way. And similarly, between processes, if you've got different programs that are running, you can choose to have address 10 million in program A correspond to an area of memory that is actually a different address in another process. And that way, those two programs can communicate with each other just by writing to an area of memory, which you have purposely pointed at the same physical block of memory. And that's super convenient for, we talked about this for, like our video, our webcam is a sort of special case of that where it's writing to memory. It could be another process that's doing this. And so this is a very, very flexible arrangement. And you did ask about whether or not, we always follow this all the way through. Some CPUs will let you say, no, actually, having reached 1, 2, 3, 4, this now giant chunk of the address space all maps to the same large area of memory. Other systems can let you configure the size of the pages. So the typical thing that we'll do in, say, high performance computing is that we'll use 2 MB sized slabs of memory, and we'll put certain amount of very big data. So, your big floating point arrays that you're going to use for your machine learning or whatever, you're putting these giant slabs of 2 meg of contiguous physical memory, and then you can map them slightly higher up. And that has two benefits. One, you don't need quite as many page table entries, and that's better. And secondly, the TLB over here, which only has 128 entries or 256 entries, if they're all only 4K entries, then that's not very much sort of memory space that you can map. But if lots of them are 2 MB slices, then that's a lot better, and you tend not to you make more effective use of the TLB in that situation. There's some things to do with pre-caching as well, but that's gets even more complicated, as this whole subject does. It's so cool and interesting. And it's going to be lots of clever instructions that I don't know how to write off the top of my head, that actually calculate the square root of whatever is in T2, as it happens. We'll come back to that in a sec. And so this instruction at line 1003 wouldn't be a square root. It would be something like call